video from the Navy shows what may be the future of modern close-in warfare. It's their new laser gun, which is shown hitting targets on ships at sea and shooting a drone out of the sky.
When news broke that the United States had successfully tested a $500 million laser system, the scientific, defense, and geopolitical communities stopped to pay attention. For decades, directed energy weapons had existed largely as theoretical projects, ambitious sketches of what might one day become possible. The image of a powerful laser beam cutting through the sky has long been associated with science fiction, but the transition from speculative fiction to military reality has been steadily inching forward. This latest test, however, represents not only a milestone but a turning point. It wasn't merely an incremental step in weapons testing, it was a demonstration that showed the world how far the United States has come in making laser technology a viable, deployable, and devastatingly effective system. Before we start, smash the like and subscribe buttons for more updates. The laser tested in this program carries immense symbolic weight. Beyond its eye-watering $500 million development cost, the system embodies years of research in optics, power generation, advanced cooling, and precision targeting. The demonstration itself sent shockwaves across the globe not only because it confirmed functionality, but also because it revealed capability. The United States had showcased in real time that it now possesses a weapon capable of projecting precise beams of energy at the speed of light, instantly striking and neutralizing threats before they even have a chance to reach their targets. In a world where reaction times are often measured in seconds, a weapon that delivers its punch in nanoseconds is a profound shift in military power. The implications begin with the simple but overwhelming physics behind lasers. Unlike traditional weaponry, which relies on kinetic impact or explosive force, lasers rely on concentrated energy. The moment the beam locks onto a target, energy is transferred directly into the material, heating it, destabilizing it, and ultimately destroying it. This precision eliminates the guesswork of calculating ballistic arcs, wind resistance, or gravitational pull. It also drastically reduces the margin for error in high-stakes engagements. In the test, the laser system demonstrated it could track, engage, and disable targets moving at extraordinary speeds. Observers and analysts understood instantly what that meant. Drones, missiles, and even aircraft that once relied on sheer velocity to avoid interception are now vulnerable. The fact that this laser weapon cost $500 million also points to its scale and sophistication. This wasn't a proof-of-concept toy or a laboratory curiosity. The United States has invested in building an operational platform that integrates seamlessly into its existing defense infrastructure. That price tag covers not only the laser itself, but the massive engineering challenges of creating the power sources required to sustain such energy output. Generating and maintaining the necessary energy levels is not trivial. It requires innovations in compact power storage, rapid discharge systems, and advanced cooling mechanisms to prevent the system from burning itself out. Each of these areas of engineering represents breakthroughs that have implications far beyond military use, spilling into civilian energy grids, industrial machining, and even space exploration. The strategic implications, however, are what truly shock the world. Lasers fundamentally change the calculus of defense. Traditional missile defense systems rely on launching interceptor rockets, each of which can cost millions of dollars per use. By contrast, a laser system only requires electrical power. Once developed, the cost per shot is negligible compared to firing a missile. This creates an asymmetric advantage. Adversaries can spend millions building and launching offensive weapons, only to have them neutralized by a near-costless burst of light. For nations considering missile salvos or drone swarms, the presence of such a defense makes those tactics economically unsustainable. The demonstration also speaks to the psychological impact of lasers as weapons. To see an invisible beam silently and instantly cut through a threat is profoundly unsettling. There is no roar of engines, no explosion of gunpowder, no streak of interceptor rockets racing skyward. Instead, there is only silence, precision, and inevitability. The weapon's invisibility adds to its aura. By the time one realizes it has been fired, it is already too late. In the test, targets were destroyed with a clinical efficiency that reminded the world that warfare is evolving into a new dimension, one where traditional expectations no longer apply. Global reaction was immediate. Military analysts across rival nations began recalculating their defense strategies. The testing revealed more than American ingenuity. It signaled a new arms race. Other nations that had been quietly experimenting with their own directed energy programs now face the reality that the United States has leapt ahead. For countries heavily invested in ballistic missile stockpiles, this technology represents a threat to the very foundation of their deterrent strategies. If missiles can be rendered obsolete at the push of a button, then years of accumulated power projection tools lose their value overnight. The $500 million test also demonstrated more than battlefield utility. It highlighted the versatility of directed energy. The same system that can strike down incoming missiles can also disable surveillance drones, blind sensors, or even knock satellites out of orbit. In a modern world dependent on satellites for communication, navigation, and surveillance, the mere hint that lasers might be capable of targeting assets in space is enough to cause alarm. For adversaries, it forces a complete re-evaluation of space-based infrastructure and the vulnerability of orbital systems. For allies, it offers reassurance that the United States can shield shared assets from hostile interference. At its core, this test proved one crucial point. The battlefield of the future will not look like the battlefield of the past. The presence of a deployable, combat-ready laser weapon fundamentally alters military planning. Aircraft formations, missile deployments, and even naval strategies must all be reconsidered when faced with the prospect of instantaneous, precise, and nearly costless counterattacks. Warships that once bristled with missile silos and artillery now face the possibility of replacing or augmenting them with energy-based defense turrets. Fighter jets that rely on stealth or speed for survival may find those advantages nullified when a laser beam can track and disable them regardless of speed or radar profile. One of the most overlooked aspects of this test is how it redefines distance in warfare. Traditional weapons are bound by ranges. Bullets eventually fall, missiles eventually run out of fuel. Lasers, however, move at light speed and can theoretically strike at any distance within line of sight. While atmospheric interference such as dust, rain, or fog can reduce efficiency, the principle remains. If it can be seen, it can be hit instantly. That reshapes how militaries will think about geography, defense perimeters, and engagement strategies. It collapses the time between detection and engagement to nearly zero, leaving little room for evasive maneuvers. The global shock also arises from the broader message behind the test. A nation does not publicly demonstrate such a capability unless it intends to send a signal. The United States, by revealing this achievement, effectively announced to the world that it has reached a level of technological dominance that others will struggle to match. It was not simply a test, it was a statement of intent, a declaration of technological superiority designed to deter potential adversaries. By showcasing the weapon, the U.S. made clear that any attempt to challenge its strategic dominance will be met with capabilities that border on science fiction. What this means for future conflicts cannot be overstated. Lasers eliminate many of the logistical bottlenecks that plague conventional warfare. No longer must militaries rely on transporting mountains of ammunition, storing volatile explosives, or worrying about resupply chains vulnerable to attack. Instead, they can focus on securing power sources, knowing that as long as energy is available, the weapon can continue to fire indefinitely. This endurance factor alone tilts the balance of prolonged engagements, where attrition has historically decided outcomes. The excitement and anxiety generated by this test also ripple into civilian scientific circles. Breakthroughs in high-energy optics, adaptive mirrors, and power efficiency achieved during the development of this weapon are likely to spill over into fields such as telecommunications, energy transmission, and even medical technology. History has shown that military research often seeds innovations that transform civilian life, and the technologies underpinning this laser system are no exception. While the weapon itself will remain classified and restricted, the fundamental advances it embodies may soon reshape industries far removed from the battlefield. For now, the test remains the focal point of fascination and speculation. Watching a $500 million system unleash its beam into the skies was more than just a demonstration of hardware. It was a demonstration of inevitability. The future of warfare will no longer rely solely on metal and explosives, but on photons, power, and precision. The entire world now grapples with the realization that the age of directed energy has truly begun, and the United States has made its opening move in a way that no one could ignore. The laser test that the United States conducted did more than confirm a new line of defense. It shattered the expectations that many experts had regarding the pace at which such technologies could be brought to operational maturity. For decades, the hurdles were considered almost insurmountable. High-powered lasers were thought of as science projects, spectacular in the laboratory but impractical in the harsh realities of the battlefield. The sheer energy requirements alone made most prototypes unfit for deployment, and the issue of accuracy in variable environments like the open sky or at sea seemed like a permanent barrier. Yet with the unveiling of this $500 million program, the United States has shown that it has not only tackled those challenges, but also mastered them in a way that opens new dimensions of warfare. What makes this achievement particularly staggering is the degree of integration between advanced science and military engineering. Lasers rely on an extraordinary level of precision in optics. The beam must remain coherent over long distances, its energy concentrated enough to inflict damage without dissipating into the surrounding air. Achieving that requires adaptive optics, specialized mirrors, and feedback systems that can adjust to atmospheric turbulence in real time. The fact that the US system succeeded in hitting moving targets demonstrates that those refinements have reached an operational threshold. It is one thing to fire a laser into controlled air. It is quite another to sustain accuracy when the atmosphere itself is shifting with wind, temperature gradients, and moisture. This success suggests that the US now possesses some of the most advanced optical compensation systems ever created. The development of this system also points to enormous advances in thermal management. A high-energy laser generates immense heat, and without effective cooling, the components would warp, crack, or burn out. Traditional cooling methods are insufficient for such energy densities, meaning the engineers had to create entirely new approaches. The system likely relies on a combination of liquid cooling loops, heat exchangers, and possibly even advanced materials with unprecedented thermal conductivity. These innovations are not minor achievements. They represent a new frontier in material science and energy systems. In fact, it is not hard to imagine these same solutions eventually revolutionizing other technologies that rely on managing extreme heat, from nuclear reactors to spacecraft propulsion. The power requirements are another area where the test defied expectations. To maintain a beam powerful enough to destroy hardened targets, the laser needs an uninterrupted and highly stable energy source. The solution is not as simple as plugging the system into a conventional generator. Power must be delivered in bursts, with precise regulation to prevent fluctuations that could destabilize the beam. The United States invested in new compact energy storage systems that can release massive amounts of power in an instant. These systems are likely based on hybrid capacitor battery technologies, combining the energy density of advanced batteries with the discharge rates of supercapacitors. Such breakthroughs could ripple far beyond weapons development, influencing electric grid stabilization, electric vehicles, and renewable energy storage. While the science and engineering are awe-inspiring, the strategic ramifications are even more profound. For centuries, the dominant theme in military power has been the balance between offense and defense. Offensive technologies, whether cavalry charges, artillery barrages, or missile salvos, have usually been countered by defensive systems that tried to keep pace. Rarely has defense leaped so far ahead of offense that it fundamentally threatened the latter's relevance. That is exactly what this laser system does. By offering a virtually limitless number of shots, instantaneous engagement, and near zero cost per use, it undermines the economic and tactical logic of many offensive strategies. It is no longer enough to build faster missiles or more drones. Adversaries must now consider that every one of those assets could be neutralized before reaching its target. This reality has already triggered intense speculation about how rival powers will respond. Russia, long reliant on its vast stockpile of missiles as both a deterrent and a bargaining chip, now faces a future in which its arsenal might be drastically less threatening. China, which has invested heavily in drone swarms and hypersonic missiles designed to overwhelm defenses, must reevaluate the viability of those systems in light of this American breakthrough. even smaller nations that have invested in asymmetric warfare, hoping to use cheap drones or rockets to balance against technologically superior foes, may find their strategies collapsing. In every corner of the globe, military planners are now calculating what it means to operate in a world where lasers stand guard. Naval warfare stands to be one of the most immediately affected arenas. Warships, often seen as floating fortresses, have traditionally been both powerful and vulnerable. Missiles and torpedoes have been their greatest threats, with interception systems like the Aegis combat system working tirelessly to provide protection. But interception by missile or cannon has always been costly, both in terms of money and in terms of limited ammunition. A warship equipped with a high-powered laser, however, can defend itself indefinitely as long as it maintains power. Incoming missiles could be burned out of the sky before they even approach, and drone swarms could be obliterated within seconds. This makes naval fleets far more resilient, altering the balance of power on the seas. Nations that once threatened U.S. naval supremacy with missile barrages must now grapple with the possibility that those barrages may no longer be effective. Air warfare, too, is poised for a radical shift. Fighter jets designed to evade and outrun traditional weapons are ill-prepared for a beam that moves at the speed of light. Even stealth technology offers no protection, because a laser does not rely on radar cross-sections to track its target. It uses optical and infrared sensors. This raises the possibility that entire doctrines of aerial supremacy may need rewriting. For adversaries that have invested heavily in stealth aircraft, the prospect of their jets being neutralized instantly by lasers is chilling. For the United States, it means air dominance could become even more secure, supported by laser systems that create protective shields over both ground installations and aircraft carriers. The implications extend into space, a domain increasingly contested in the modern era. Satellites are vital for communication, surveillance, and navigation. Until now, they have been largely immune to attack due to their altitude and speed, but a sufficiently powerful laser, directed from the ground or from high-altitude platforms, could disable or destroy satellites with precision. The test itself may not have included orbital targets, but the world understands that the same underlying technology can be adapted for such use. The specter of anti-satellite warfare, once confined to kinetic interceptors and missiles, now includes beams of coherent light, capable of rendering orbital assets useless. This changes the strategic landscape of space, introducing uncertainty about the survivability of satellites in future conflicts. Beyond the battlefield, the successful test also symbolizes the culmination of decades of persistence. The United States has pursued laser weaponry since the Cold War, with projects often ridiculed as money pits or unrealistic fantasies. Critics pointed to the enormous costs and technological hurdles, dismissing each program as doomed to failure. Yet, with this test, those doubts have been silenced. It is a reminder that military research often requires patience, with breakthroughs sometimes decades in the making. The $500 million invested here represents not just money, but the accumulation of knowledge from countless failed prototypes, incremental advances, and tireless experimentation. The demonstration is a vindication of that long journey. From a global perspective, the test also raises urgent questions about arms control and international security. Lasers, by their very nature, blur the line between defensive and offensive capabilities. While they are promoted as protective tools, capable of shielding cities and bases from attack, they also possess offensive potential that is difficult to ignore. The ability to disable satellites or blind sensors can cripple an enemy's capabilities without firing a single traditional shot. How will treaties and agreements account for weapons that leave no ballistic trajectory, no explosive residue, and in some cases no visible evidence of their use? The demonstration has forced policymakers worldwide to confront questions about how to regulate a technology that defies traditional categories. There is also the moral and ethical dimension to consider. Lasers promise clean, precise strikes, often with minimal collateral damage compared to missiles or bombs. That makes them attractive from a humanitarian standpoint, as they could theoretically reduce civilian casualties. However, their precision also makes them tools of silent dominance. They can disable infrastructure, sensors, and vehicles without the spectacle of explosions, creating a form of warfare that is less visible to the public and perhaps more tempting for governments to use. The invisibility of such weapons may make conflict more palatable to leaders who wish to avoid public scrutiny, raising concerns about the threshold for war being lowered. The unveiling of this system also underscores the deep integration between military ambition and industrial capability. Developing such a weapon required not just government funding but also partnerships with private industry, research institutions, and universities. It reflects the vast ecosystem of innovation that the United States can mobilize when pursuing national security goals. The ripple effects of this collaboration are likely to stimulate entire sectors of the economy, from advanced materials to high-energy physics. This fusion of military demand and civilian innovation is part of what makes the achievement so striking. It is not just a weapon, but a catalyst for broader technological growth. For rivals and adversaries, the test represents a challenge that is both technological and psychological. On the technological side, catching up will require investments of similar scale, along with access to the scientific talent and industrial base needed to replicate such a feat. On the psychological side, the mere knowledge that the United States can deploy lasers shifts the calculus of deterrence. Even if rivals eventually build their own versions, they must grapple with the time lag in which the US enjoys a monopoly. That interim advantage could shape geopolitical negotiations, alliances, and strategies in profound ways. The test also sends a clear message about priorities. In an era where cyber warfare, artificial intelligence, and hypersonic weapons dominate discussions, the United States has chosen to emphasize directed energy as a cornerstone of its future arsenal. This signals to the world that the US does not view lasers as fringe or experimental, but as central to its vision of modern warfare. Other nations now face the question of whether to follow suit, pouring resources into catching up, or to pursue alternative strategies that bypass the directed energy domain. Either path is fraught with risk, but ignoring the technology altogether may no longer be an option. The demonstration of the United States' $500 million laser system was not just about unveiling a new weapon, it was about rewriting the limits of what energy-based systems can achieve. To understand the magnitude of this moment, one has to look beyond the immediate spectacle of a beam slicing through targets and consider the cascade of possibilities it opens across multiple domains. Each aspect of this test forces a reevaluation, not just of military balance, but of science, strategy, and human imagination itself. One of the most striking elements lies in the weapon's adaptability. Unlike missiles or artillery, which are designed for specific ranges and purposes, a laser weapon can scale its output depending on the target. It can be dialed down to disable electronics without physical destruction, or it can be unleashed at full power to melt through reinforced structures. This variable intensity means it can operate across a spectrum of engagements, from non-lethal suppression to catastrophic neutralization. The precision of this controllable escalation is unprecedented. For instance, in a contested urban environment, a laser could disable a hostile drone without detonating an explosive that might endanger civilians. In contrast, on a battlefield, it could deliver overwhelming force to eliminate hardened threats instantly. The very versatility of the system makes it a unique tool, unmatched by conventional weapons. Another underappreciated dimension is the psychological impact on adversaries who now know that line of sight effectively equals vulnerability. The knowledge that a target can be struck instantly, without warning, without evasion, changes the psychology of warfare. Traditional tactics rely on maneuvering, cover, and speed, but against a weapon that functions at light speed, none of these defenses hold. For drone operators or missile crews, the realization that their weapons can be neutralized before impact erodes confidence in their missions. This psychological disruption can be just as effective as the physical destruction, undermining morale and making adversaries hesitant to commit assets. The demonstration also highlights the role of automation and artificial intelligence in modern warfare. A high-powered laser system does not function in isolation. It depends on advanced tracking, targeting, and decision-making systems that can process vast amounts of data in real time. The speed of light engagement demands that detection and targeting occur almost instantaneously. Humans, with their natural delays in reaction, cannot keep up. Therefore, the laser system must be integrated with AI-driven platforms capable of distinguishing friend from foe. predicting trajectories, and initiating strikes within fractions of a second. This convergence of AI and directed energy marks a new stage in autonomous defense. It blurs the line between human oversight and machine action, raising questions about how much decision-making is entrusted to algorithms in lethal engagements. The ripple effects on defense logistics are also extraordinary. Armies traditionally plan around ammunition supply chains, how to store it, move it, and protect it. Ammunition shortages have determined the outcomes of countless battles throughout history. A laser weapon alters this fundamental constraint. Instead of stockpiling shells and missiles, the focus shifts to ensuring uninterrupted power supply. This simplifies logistics enormously. A mobile platform with sufficient onboard energy generation, such as nuclear-powered ships or vehicles equipped with advanced batteries, could theoretically sustain unlimited defensive fire. The liberation from traditional ammunition chains changes not only battlefield endurance, but also strategic planning at the highest levels. Wars of attrition, where victory often depended on exhausting an enemy's ammunition, may become relics of the past. Consider the aerospace industry as another sector that will inevitably feel the impact of this milestone. Civilian applications of laser technologies have long been limited by cost and efficiency. However, the breakthroughs required to make a $500 million weapon viable, advances in energy storage, optical materials, and atmospheric compensation, can also revolutionize non-military uses. For example, space exploration could benefit enormously from the same technologies. Lasers could be used to propel light sails for interstellar probes, transmit energy to spacecraft without carrying heavy fuel loads, or even provide communication systems with previously unattainable bandwidths. By perfecting these systems in the context of defense, the US has effectively accelerated capabilities that could redefine humanity's reach into space. The test also opens the door for reconsidering defense in the context of homeland security. One of the greatest threats to modern nations is the rise of low-cost drone swarms, which can be deployed by both state and non-state actors. These swarms overwhelm defenses not through sophistication, but through sheer numbers. Conventional anti-aircraft missiles cannot realistically counter hundreds of drones at once without enormous expense. A high-powered laser system, however, could sweep through such swarms with precision and minimal cost per shot. This has immediate implications for protecting critical infrastructure, power plants, government buildings, airports, from terror attacks or sabotage. The ability to defend urban environments from airborne threats could transform domestic security policies. Even beyond Earth's atmosphere, the implications are staggering. The demonstration confirmed that the technology is mature enough to consider orbital applications. Space-based laser platforms could serve as global defense systems, intercepting threats before they even reach national borders. Imagine a constellation of satellites equipped with directed energy weapons, forming a protective shell around the planet. The US test doesn't yet represent that stage, but it is the first undeniable step toward it. For adversaries, this raises the chilling possibility of being surveilled and defended against from above with no effective countermeasure. For allies, it raises hope that shared defense shields could one day protect entire regions. Another dimension worth noting is the impact on industrial competition. The defense industry thrives on contracts, and the demonstration of this laser system is certain to ignite competition among contractors eager to develop the next generation of directed energy weapons. Companies specializing in optics, energy storage, or aerospace will now race to secure their place in this burgeoning field. This arms race within the private sector could produce rapid advances, not just in weaponry, but in spin-off technologies that feed back into civilian markets. In some ways, this mirrors the digital revolution of the late 20th century, where military research into computing laid the groundwork for the modern tech industry. At the international level, the demonstration forces allies to rethink their own roles in collective security frameworks. NATO, for instance, has long relied on a shared missile defense architecture. But if lasers replace missiles as the cornerstone of defense, how will member states adapt? Some nations may lack the resources to develop such systems independently, creating a dependency on American technology. This could reshape alliance dynamics, with the US holding an even more dominant role in collective defense. It may also prompt calls for technology sharing agreements, though the strategic value of directed energy makes such sharing unlikely in the near term. Equally important is the impact on non-state actors. Groups that once hoped to use cheap rockets or drones as asymmetric weapons will find those strategies neutralized. This forces a shift in the landscape of unconventional warfare. The balance that once allowed smaller groups to challenge larger militaries through ingenuity and mass may no longer hold. Instead, they will have to explore entirely new tactics, perhaps focusing on cyber warfare or other domains where lasers have no reach. In this sense, the US test indirectly reshapes the future of insurgencies and terrorism, closing one chapter while potentially opening another. From a scientific perspective, the test is also a demonstration of humanity's ability to harness and control one of the most fundamental forces of nature, light. For thousands of years, light was understood as illumination, a source of vision and warmth. To bend it into a weapon of such precision and power represents a symbolic shift as much as a technological one. It is a reminder that human ingenuity continually redefines what natural forces can be used for. Just as fire, once only a source of heat, became the basis of engines and explosives, so too has light evolved from guidance into a tool of defense and dominance. This test also highlights the growing importance of interdisciplinary collaboration. No single field could have achieved this outcome alone. Physicists, engineers, computer scientists, materials specialists, and military strategists all had to converge on a shared goal. The system embodies the culmination of multiple disciplines working in harmony, each solving problems that seemed insurmountable in isolation. This model of integrated research is likely to be emulated in other grand challenges, whether in climate change, medical research, or space colonization. The demonstration thus serves as proof that human progress is most rapid when diverse fields are aligned toward a single ambitious target. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on the US testing its $500 million laser technology? We want to hear from you. Thank you for watching, and see you next time.